videos, we have covered the concept of standard uncertainty and discussed its meaning. In order to make practical use of these concepts, it is necessary to understand which methods should be used to assess standard uncertainty in practice. Once again, the GAM helps us by defining two evaluation methods that are referred to as Type A evaluation method and Type B evaluation method. The Type A evaluation method is defined as a method of evaluation of uncertainty by the statistical analysis of series of observations. The Type B evaluation method is defined instead as a method of evaluation of uncertainty by means other than the statistical analysis of series of observations. As a matter of fact, the Type A method follows a frequentist approach to processing the available data, whereas the Type B method follows a Bayesian approach. For reasons related to the historical period in which the GAM was conceived, it was preferred to use generic names and definitions. In this lesson, we will analyze the Type A method, which is based on n independent observations. We have seen that a measurement result is represented by a random variable, which we will call capital X. Let's suppose we repeat the measurement of the same measurand under the same measurement conditions n times. We'll have n observations small xk of variable capital X. Probability tells us that the best estimate, also known as the expectation of X, is given by the mean value of the n observations, a mean value which is obtained from the formula you see here. In the absence of systematic errors, as initially assumed, this mean value provides a better estimate of the measurand than any of the measured values xk, and is therefore taken as the numerical value of the measurement result. To obtain a measurement result, we must also be able to evaluate the standard uncertainty, that is, the standard deviation of the random variable capital X. Let us remember that the standard deviation represents the dispersion of the values that could be attributed to the measurand. An estimate of the standard deviation, also known as the sample standard deviation of X, is obtained from the n measured values small xk and their mean value by applying the formula you see here. Can we assign the value obtained to the standard uncertainty? This value represents the dispersion of each individual measured value xk. However, we are indeed interested in the dispersion of the mean values that we can obtain through repeated series of n observations. Mathematics helps us here. It shows that the standard deviation of the mean values is obtained by dividing the sample standard deviation by the square root of the number of observations, as you can see here. These, as we have seen, are the steps needed to arrive at a Type A evaluation of standard uncertainty. Let's now see how to put this into practice with real instruments. Here we have a digital multimeter, which we will use as a voltmeter to measure a DC voltage. Next to it, there is a voltage generator that we will use to generate the DC voltage measured by the voltmeter. These instruments can be controlled by a PC, which can read the measured values and then process them. I have set up a Python program that makes the generator produce a voltage and then reads a certain number of values measured by the voltmeter. In this experiment, we generate a voltage of 8 volts and have the multimeter read 30 values. Let's start the program. The PC is reading the 30 values. As soon as it has finished, it computes the mean value and the sample standard deviation, then divides it by the square root of 30 and gives us the Type A evaluated uncertainty value. There we are, it's finished. And we can see that the mean value is 8.00746 volts, The sample standard deviation is 55 microvolts, and the standard uncertainty is 10 microvolts expressed with only two significant digits. Let's start it again and have it acquire another 30 values, so we can also see experimentally that the mean value we obtain now is slightly different from the one we just got, and therefore it makes sense to evaluate the dispersion of the mean values rather than that of the individual ones. Now that the second run is finished, we see that the mean value is 8.00744 volts, the sample standard deviation is 56 microvolts, and the standard uncertainty is 10 microvolts. We therefore notice that the mean value has changed, but the standard uncertainty has remained practically the same. To summarize, we began to discuss the methods recommended by the GAM for evaluating the standard uncertainty. We analyzed the type A method, that is, the one based on the statistical analysis of a series of observations, and we saw how it can be used in practice. In the next video, we will analyze the type B method.